So one of the things that might be useful for you to know before you take the exam on Thursday is how to sum up vectors to get an E field. So what do I mean by that? Let's talk about a specific example. So here is an example. Imagine we've got some charges arranged like this. A 2 microcoulomb charge on this corner of the rectangle, a -3 microcoulomb charge on this corner, a +2 microcoulomb on this corner. And then we want to know what the electric field is at this point P right there. And we're given distances between these charges, 3 meters, 4 meters, 3 meters, 4 meters. How are we going to get something like that? How do we know? So one of the things that we can do is first try to estimate what's happening in this situation. So let's just take a look at what we think is going to happen in terms of the E field. Now remember that the E field lines go in the direction that a tiny positive test charge would move. So if I put a tiny positive test charge near this 2 microcoulomb charge over here on the upper right corner, what would happen is it would move to the left away from that 2 microcoulomb charge. It would basically move, in this direction. And so that's going to cause a contribution to the E field at this point here, looking something like that. Now, if I put a tiny test charge near this 2 microcoulomb down here, what it would do is it would move away from it like that. Now, this is going to cause a contribution at point P looking something like this. Now, why am I drawing that line a little bit longer? Because the distance between this 2 microcoulomb charge and this point P is not as much as the distance between this 2 microcoulomb charge and this point. So the electric field of a point charge falls off in magnitude as you get further and further away. So that's why these contributions are of different magnitudes. So now let's consider this point down here, the 3 microcoulomb charge. So if I put a test charge right here, it would be drawn in. It would be drawn into this guy, okay? So if I'm over here at point P, then what that means is I'm going to basically be drawn in that direction. So it's going to look something like that, right? So these 3 arrows are rough estimates of what we're going to find. And notice also that the length of this guy here, go back. The length of this one is biggest because it's closest. This one is maybe next largest, and this one should be the smallest. Maybe I haven't drawn it perfectly, but anyway, you get the rough idea. It's going to look something like that. And if we want to estimate what these guys are going to look like if we add them together, remember what we do is we add vectors from some point of the origin. So let me add the first one. So the first one looks something like that, okay? And then I'm going to pick another one, and let me just put another one right there, okay? That's the second vector, that is this one here going to the left. And now I'm going to add this vector here. And I take the tail of this vector and I basically put it on the tip of that one there. And so I get something that looks roughly like that. If I add them, just tail to tip, something like that. And then what that means is I would get, in estimation, a vector that would go from the origin to the end of this chain. So it's going to look something like that. That's our estimation. And so I drew that over here, looks like that. So that's the vector sum right there. I drew that a little bit beforehand by actually clipping these vectors that I sketched up above. And with the wonderful iPad, I can take those very things and line them up like that in a chain. So that's the estimation part. So we expect a vector that goes almost straight up and a little bit tilted to the left. Now what we have to do is calculate. We're going to calculate each component one by one. And so we want to calculate this component that I've circled in blue, and that's just the contribution only from the positive 2 microcoulomb charge on this point here. We want to know what its electric field contribution is. So we're reminded that the equation for the electric field of a point charge is given by this. It's equal to kq over r squared. So I want to know what the magnitude of this charge is. That's what my q is going to be. And I want to know what the distance r is between these points. That's what my r is going to be, like that. So I plug in these values, and k is a constant. We'll always give you that on the exam. 9 times 10 to the 9th Newton meters squared per coulomb squared. Multiply that by the charge. So this is k times the charge times r squared. And if I punch all that through, I get this number, 1125 newtons per coulomb. So that's a valid way of measuring the E-field strength. You could also measure it in volts per meter. These units are basically equivalent. And we note that this is going in the minus x direction, right? Because a positive charge is going to be pushed away from that point and toward point P. That's in the negative x direction. Okay, what about another one? So let's try to calculate this one. We're going to calculate each one as a vector and then add them all up at the end. So this vector here is coming from this positive 2 microcoulomb charge, and it's only 3 meters away. And again, we want to know what its effect is on point P. So we go in and we use our formula. Again, it's from the point charge. The E field is going to be kq over r squared. K is that constant. Q is 2 microcoulombs, and micro is 10 to the minus 6. And the distance between these two is 3 meters, so it's 3 meters squared. You punch in all those numbers, and it's 2,000 newtons per coulomb in the positive y direction, because the E-field lines are going from the positive charge toward point P. That's the direction a small positive test charge would go if I dropped it right there. It would move that way, so it's going to cause the vector to go up like that. All right, the last one is this. What's the contribution from the minus 3 microcoulomb charge? That's further away. And you should recognize, or maybe you don't recognize, but just real quick, this is a 3, 4, 5 triangle. It's one of those right triangles that you often have to know for handy situations. And basically 3 squared plus 4 squared equals 5 squared. So that's how that works. So that is going to mean that the distance here between this charge all the way over to there is 5 meters. That's the diagonal. And so now we're going to plug those things in. So here is our equation. Again, E is kq over r squared. K is that value. Q is minus 3 microcoulombs. So that negative sign is going to be important. Don't forget it. Don't drop it. Actually, when I was first sketching this out, I forgot it. And then I noticed it in the middle of my calculation. So it's easy to do. And the distance, as we said, is going to be 5 meters because that's the hypotenuse of this 3, 4, 5 triangle that we have. So we calculate all that. Ends up being 1,080 newtons per coulomb. Now this is complicated because it's kind of pointing in the negative x direction and it's kind of pointing in the positive y direction. Or is it? What's going on? If it's the direction that a positive test charge would go in, let's just think this through. The positive test charge is going to be attracted. It's going to be attracted to this negative charge. So it's going to move in that direction like that. So it's really going in the negative y and the positive x. Okay? So that's what we have here. Negative x and positive y. All right? And now what we're going to do is we're going to try to take these components using sine and cosine. This is where the vectors get, I think, a little bit challenging for students in P202. But just a refresher, here's our triangle. Let me zoom in on this guy. This is our 3, 4, 5 triangle like this. And the angle of interest for us is this angle theta right here. Okay? We know this is 4 meters, we know that's 3 meters, and we know that this is 5 meters. That's the hypotenuse. So I can immediately get a handle on this angle, and that's going to be important for adding things up, as you'll see in a minute. So I can say the tangent of this angle, tangent is opposite over adjacent. It's 3 over 4. So if I take the arc tangent of 3 over 4, I'm going to get the angle. That's 36.9 degrees. So if you punch in 3 over 4 in your calculator, divide that, 0.75, and then press the arctangent key, this is going to pop out. So that tells us what the angle is. That's useful because now what I can do is I can take this, which is the magnitude of that vector that's going across the diagonal here like that. I can take the magnitude of that vector and I can multiply it by sines and cosines to get the components of the vector. So if this is our angle theta right here, then the opposite side is going to be this. Okay, so that means the y component has something to do with the opposite side over the hypotenuse. So opposite over hypotenuse, that's sine. So ca, toa. If you haven't heard that before, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Definitely drill yourself on those things because they'll come in handy for the exam. So I can say, if I want to know this component here, that's going to involve the tangent. The sine, because that's the opposite side, okay? So what I can do is I can say the y component, which is pointing down, is going to equal the magnitude of our vector times the sine. So that's how I take the y component of the hypotenuse. And likewise, if I want to know the x component, well, that's going to be the cosine of theta. because this is the adjacent side. It's actually touching the angle, right? This side is touching the angle there. Whereas this one that's opposite is not touching the angle over there. That's how we know it's opposite. And the long diagonal is always the hypotenuse. Okay, so to get the component in the x direction, what I do is I have to take, in the x direction, I have to take the cosine. Yeah, right there. So there I am. So I take this magnitude, 1080 newtons per coulomb, and multiply it by the cosine. And I know that this is moving in the positive x direction, so I've got a positive sign there. I know that this is going in the negative y direction, so I've got a negative y sign there. So I can punch this into the calculator, multiply these guys out, and I get plus 863.7 newtons per coulomb in the x direction and minus 648.4 newtons per coulomb in the y direction. Okay, so I've got x and y components for all the vectors that we talked about when we went back and did our estimation, right? So when we estimated these different things, I know all of them. I know that this guy is purely in y, positive y. This guy is purely in x, negative x. And I know that this one here is in negative y and positive x. So now I can create a table where I separate the x and y components. So I go all the way down here, and here's my table, okay? I'm going to represent these three vectors, but now only in terms of x and y. So here's my x part and my y part. And this is the contribution from the 2 microcoulomb charge that's 4 meters away. So that's this charge here. That's 4 meters away from our point of interest, point P. All right, and the answer that we got, and you can go back in the video, but it's 1125 newtons per coulomb. And it's pointed that way, so that's the negative x direction. There is no y component to this at all. So that's just this. There's no y component to this particular charge, this one here. Now let's go to the next one. This is 2 microcoulombs at 3 meters away. So that's this guy, 2 microcoulombs here, and it's 3 meters away from that. That is only going to contribute a positive y. So I have no x component at all, but I have a positive y right like that. And now lastly, for the 3 microcoulomb at 5 meters away, so that's this guy, and its distance is 5 meters away from point P, our point of interest, where we're adding up all the vectors to get the electric field. And as we saw in the previous slide, basically we got that, 863.7 in the positive x direction, that's the x component of it, and minus 648.4 newtons per coulomb, that is the contribution in the negative y. So it's got a negative y component, and then it's got a positive x component like that, giving us a direction in a diagonal like that. Now I can take this number and add it to that number and add it to that number, and I get a total value for my x contribution. And for the y, I can add this number and this number and this number, and I get a total value for my y contribution. So think of this. It's going in the negative x direction, and then it goes up in the positive y. What does that look like? Well, it's going to look like this, okay? So here we go. This is our negative 261 in the x direction, that's this, and then positive 1351.5, which is about 1352, up like that. So if I add these vectors, so I put the first vector, I put its tail at the origin like that, and then I make it go this way, and I take the next vector and put its tail on the tip of that one and add it up like that. Then I go from the very origin all the way to the end of that chain. The chain goes this way and then up that way. And so I go to the end of the chain, and that is the direction of my resultant E vector. It looks like that. So I've got these sides, 261 and 1352. Let's call this angle alpha, so I can calculate that angle by basically saying the opposite side over the adjacent side of alpha is going to look like this. That's the tangent, opposite over adjacent. The opposite side is 1352. The adjacent side is 261. So I can use the arctangent key of 1352 over 261 to get alpha. And if I plug it in there, I get alpha equals 79 degrees. And that's 79 degrees from that corner of the triangle, okay? So that means if I'm pointed in this negative x direction, I basically rotate by 79 degrees, and then I'm going to have alpha. Now, you might ask, what is this whole angle here? Well, that angle there, if you want it, is going to be 90 degrees there, plus 90 degrees minus 79 degrees. So that would be 11 degrees. So 90 plus 11 should be 101 degrees. So it should be about 101 degrees all the way from there over to there, if you like your angle that way. Otherwise, you can report it like that, and that's perfectly fine by me. So that's the angle of this thing, but what is the length of this vector? So we got to use the Pythagorean theorem. We know that 261 is one of the sides. We know that 1352 is the other side. We want to calculate the length of the hypotenuse. So we just put these guys in, we square them, add them together, and then take the square root. And if you do that, it's 1377. So overall, the electric field starts at the origin and goes up like that. It's got a magnitude of 1377 newtons per coulomb. It's at an angle of 79 degrees from the negative x-axis, or 101 from the positive x-axis. That's fine. So hopefully this has given you an overview of how you might add up all the electric field components, if they're point charges, to figure out what the vector sum of the electric field is at a given point P, like that. So the electric field is a vector. You have to add it up like this using sines and cosines. You got to keep track of all the x and all the y. Now, if I had asked a different question, if I had said, what is the voltage at point P? Those are not vectors. There you only have to worry about the height caused by the point potentials and then at that distance, and then you add them all up. So hopefully this has been helpful to you, and let me know if you have any questions. You can leave comments below and I'll try to respond to them.